With AI agents becoming more common, it's becoming increasingly likely that instead of one AI running your entire workflow, you would have hundreds, maybe even thousands. Now imagine an entire company where every task is handled by autonomous agents. Some are researching, some are writing code, some are making API calls, some are failing, and all of them are constantly changing state. Now imagine 50,000 of them. Every second they are producing events, started, running, waiting, some are calling tools, failed, completed. Now the question becomes, how do you ingest all these events, preserve the order of each agent, update a dashboard in real time, and avoid overwhelming your database? That's what we are solving today. Hey everyone, I'm Coded. I'm a software engineer who codes a lot and thinks just as much. In this video, I would walk you through Beacon, an open source observability pipeline I built for AI agents. We'll start with a naive architecture, look at why it breaks under load, redesign it from scratch, and then I'll show you the entire system working from simulated agents all the way to a live dashboard. Let's lock in. This is how most of us will build it. We have our agent that would send events to an API. So I drop in the agent, it's dropped the system box, and these agents will send a request to an API server. And the API receives it, then stores it in a relational database. In our case, we would be using SQL since it is structured to store each state. Then that data is now saved and updated to be sent to the dashboard. Let's see this out loud. Dashboard. Once again, the agent sends the data to the server saves it in the relational database, and then the relational database updates the front end directly. Easy, right? But what happens when thousands of agents do this simultaneously? The database suddenly becomes responsible for every insert, every dashboard update, every burst of traffic. Eventually, it becomes the bottleneck. That's the problem. While thinking about this, I realized something. The dashboard does the dashboard needs events immediately. The database doesn't. This realization completely changes the architecture. So now let's redesign this. We know our database is the bottleneck, so the first thing we need to do is to get it out of the critical path. So first thing we are going to do is to withdraw our AI agents. Up here we have our AI agents. In reality, this could be anything. Coding agents, research agents, customer support agents. The important thing here is to note that they are constantly producing state actions. Instead of sending everything to one server, the first request hits a load balancer. Its only job is to distribute traffic across multiple gateway instances. So now we're going to draw the different gateway instances. The server. Behind the load balancers, we have our servers, our API gateways. These are intentionally lightweight because they validate the request, maybe they do a little pre-processing, and then they don't touch the database. This is the first major design decision. Kafka. Instead, instead of sending it directly to a database, every event gets published to Kafka. Think of Kafka as a durable event log sitting between your ingestion and your processing. The gateways don't wait for a database anymore. As soon as the event is safely written to Kafka, they can return a to accepted to the client and move on to the next request. Here's the part I found really interesting. The partition. Every event is produced with an agent ID as its key. Kafka uses that key to decide which partition each event goes to. So this agent sends its own data to this partition. This agent sends its own data to this partition. This agent here also sends its own data to its own specific partition. That means that every agent sends their own event in their own partition. Why is this important, you may ask? Because Kafka guarantees ordering within a partition. So if one agent emits started thinking, why is this important? Because Kafka guarantees ordering within a partition. So if one agent emits starting, thinking, calling it to waiting, then it's complete. That's the exact order every consumer would see. Notice that we are not guaranteeing. We are not trying to globally order events across 50,000 agents. They are running concurrently, so that doesn't really make sense. What we care about is preserving the timeline of each individual agent. Now that the events are safely inside the Kafka, we can process them independently. The first consumer group is a broadcaster, also known as a WebSocket. Its only responsibility is getting events to the dashboard as quickly as possible. It consumes events from Kafka and immediately pushes them to connected clients over WebSockets. That is how the dashboard updates in real time. But then we still need to update the database. So I'm going to draw the second under consumer group, which has a completely different job. But then we still need to update the database. I'm going to draw another consumer group that has a completely different job, the archival. So instead of optimizing for latency, it's optimizing for efficient storage. Instead of optimizing for latency, it's optimizing for efficient storage. Rather than inserting every single event individually into a database, it batches them together every 500 events, every 2 seconds, whichever comes first. Then it flushes them directly to a database in one operation. Now, if we take a look at this these two consumers don't know anything about each other. They do not block each other, they do not compete with each other. If the dashboard suddenly has 10,000 connected users, the database doesn't care. And if the database becomes temporarily slow, the dashboard keeps updating because it's directly reading from Kafka. That is the power of decoupling your system with an event log. So now our flow looks like this. The agent sends events, the gateway API servers digest them, sends them to the Kafka for storage, and orders them through our different partitions. And each partition has their own agent ID. Then the consumer streams them live through the WebSocket, and another consumer called the archiver saves them efficiently by batch storage for every 50,000 requests or every 2 seconds directly into a database. And every of these components can scale independently. Alright, enough diagrams. Let's actually run the system and watch an event travel through the pipeline from the agents to a dashboard and to a relational database. So after architecting all that with the whole data flow from the agent to the dashboard to the relational DB passing it through Kafka, let's see how the code actually looks like. So this is the beacon project folder where I separated everything into microservice architecture. So we have this shared service and the schemas, because we needed to keep state across different agents. So the schemas are outside, so it's not directly tied to one particular folder. So we have the different services that we created, the archival service and the main.py inside the archival services, which is the Kafka bootstrap, which we had already created directly in the infrastructure. So we use Red Panda for our own. You can just download it or set it up with brew install RPK. And you have the load balancers here, the code for the load balancer. You have the requirements for each and every one of them. Then you added Prometheus watchtower, which essentially shows us the status of each and every one of our services. So you can install it with brew install if you're on Mac, and the same way on Windows. Then you have the different scripts to simulate it. Then you have services and shared and the whole Docker compose. And I wrote a start.sh written in bash script so that you can actually see how it looks like without having to cover and abstract everything out with Docker, right? So you can just open up a terminal once you have cleaned the whole project. You can open up a terminal and do sh start.sh or create sh as an executable first. So we have chmod plus x start.sh, then just do ./start.sh. So now what it's going to do is that it would start up the whole project. So now it says docker daemon is not responding, so what we need to do first is start up docker. So docker is running in the background. We have docker open up. This is the Red Panda already running, created 48 days ago. So after installing, you can start with rpk container start, but instead of doing that, our bash start script already contains the Red Panda image and when to start. So all we just need to do is to run the executable start.sh file. So it's going to first start installing the Python dependencies if you do not have it installed. For me, I already have it installed at the .venv virtual environment. Then next, it's going to ensure that Docker is started up. Then it will start up Red Pandas. That is what it's currently doing. Then it will now create the Kafka topic and the whole gateway instances. So the dependencies have been installed. It's starting up Red Pandas. So now all the services are started. So Red Panda is started. It has created a Kafka topic called agent state transitions and the different gateways. For now, I only set it to have 2 gateways, and our load balancer run on ports 8000 with the 2 gateways at 8010 and 8011, and the archiver at 8002, broadcaster 8001. So it actually follows the whole microservices architecture that was intended from the start. So then we have Prometheus set up, and Yeah, beacon is live. So the next thing that we can do now is to run the front end npm run dev after installing all the required libraries and modules. So now it is running at port 5173. Then now you can just go over here and click on it up, and now we have each status and each service gateway. So if you check the feed, currently it says nothing is showing, right? Because we are not actively passing any data into the beacon, right? So what we will do next is to simulate the entrance of data and simulate agents into it. So if you actually go through the readme, you would see here where it says you can fire 10 agents at 2 events per second, and you can crank it up so up to 100 agents at 500 agents per second. So what I'm going to do is I'm going to copy the command here and paste directly in beacon. Then we press enter. So what it's going to do now is going to simulate 10 agents at 20 events per second. So if you look at the terminal here, it says flushed one root db. So what it's doing is that it is actively sending this data directly to the database. So now if we check that front end again, now you can see it's actually sending data. So now these are the 10 agents, though it is constantly keep changing, updating from 1 to 3, 1 to 3, 4, 5, 6, 7, 8, and the different events here. So it is updating at 32 per second. Note that the difference between it being 20 events per second and 34 per second takes into consideration the network lag and other factors outside the request and response cycle. And with that, you can actually crank it up, add more agents to it, and increase the whole rate. So I'm just going to stop all of them now. This isn't really a project that I wanted to git keep. I think more people are going to be building systems around AI agents over the next few years. So rather than making Beacon another portfolio worthy project, I decided to make it open source. So if you want to improve it, replace components, benchmark it, or even use parts of it into your own project, I'd love to see what you build. If you enjoy this kind of systems content, consider steering the repository. It really helps. And if you got a question, an idea about the architecture, you can always drop them in the comment section. Thank you for watching, and I'll see you in the next one.